I always wanted to run out on a stage like a professional athlete, with the things going on in the background. I actually just completed my first marathon 3 weeks ago, so I'm in good shape, ready to go. The theme of the conference is decoding the future, and I wanted to touch on that theme in my first set of slides by pointing out that the future really isn't what it used to be. And by that I mean that in some sense, if you look back in the past, in those days when we looked forward to the future, we had very different perspectives on where we would be today. I came across this quote in a review of a book called Slant, science fiction book from the 1940s. And the point here was that it's very charming how people in the past thought about the future. We somehow didn't wind up with roads that flow through the air. We didn't wind up with flying cars, and certainly the International Space Station doesn't look quite that interesting as they had on the 2001: A Space Odyssey. Of course, there were a number of predictions that were made, in particular in science fiction, in the 1940s and 50s and early 60s that did come true. Arthur C. Clarke, in an early story in the 1940s, described the first communications satellite, which of course was not launched for several decades afterwards. In Star Trek, in the TV series, they had a device called a communicator, and you could flip it open and you could talk to people almost anywhere. And that seemed really like science fiction. But of course, today we all have cell phones, and we communicate with people all over the world, anytime that we want. Of course, another concept that you may have seen, this was also in Star Trek, but in many other science fiction stories from the 1950s and the 1960s, is this concept of a data crystal. And that's come true as well. And I say that, and then sometimes when I say that, people will say, but wait a minute, we don't have data crystals. And the answer is we do, right? I have gigabytes of information stored on silicon crystals on a USB stick that I keep with me. So we were able to create that as well. Of course, sometimes when people predict the future, even very smart people, they get it very wrong. So here's a quote from Thomas Edison. Fooling around with alternating current is a waste of time. No one will ever use it. Well, obviously that didn't turn out to be true. Here's another quote from another very, very smart person, Albert Einstein, who questions the possibility that we would ever be able to harness nuclear energy. Even sometimes predicting something like future real estate trends can be very, very difficult. Here's a quote from Arthur C. Clarke in an issue of Vogue magazine in 1966, where he makes some predictions about what the world might be like in 2001. And, well, that didn't quite happen. Houses aren't quite able to fly unless you count the house in the movie Up with the balloons. And for the most part, cities don't migrate from one part of the country to the other. So that didn't quite happen either. Here's a quote from T.J. Watson from 1943, sort of looking at what the future might be like. And Watson said, well, maybe in the future there'll be opportunity for 5 computers. That turned out not to be very accurate. Even John von Neumann, in a quote in an article in 1949, made the comment that it would appear that we've reached the limits of what's possible to achieve with computing technology. Well, that didn't quite work out either. Of course, there were very optimistic predictions on what computers might be. Here's one again from 1949 in Popular Mechanics magazine, where they predicted that someday they could imagine that computers might weigh less than 1.5 tons. I don't think I would be carrying around a 1.5 ton computer. I don't think that would be very, very hard. Of course, if you actually read the full quote from John von Neumann, what he really said was that we may be reaching the limits of computing technology, but that you have to be careful with the predictions that you make, because you can look very foolish in 5 years. And, that prediction did look very foolish in 5 years. Here's another prediction. This is from Kent Olson at the no longer existent Digital Equipment Corporation, saying he thought there'd be no reason one would want a computer in their home. Well, of course, just a few years later, the IBM PC was released and became the basis of what eventually was, the home computer and home computing. And so that obviously turned out very differently than what Kent Olson was predicting. Now, it isn't just that we can't predict, when a technology is going to come into existence, or how the technology will impact a particular segment. But often we don't understand how a technology will be used. So people in the early days of computing tended to think of computing as being something very lofty, that it was going to be focused on solving really hard problems. And they didn't realize that it could be used for other things as well. So what I'm about to show you is a commercial that was aired in the 1990s for a computer graphics company, where they make fun of that idea.
Here we are using technology to save the planet. Our tiny chip, it does 100 billion operations per second. That is our most awesome. And we are using it to make a difference. Imagine clean air, pure water, and a new future. I wish my family back home could see me now. And we are most proud knowing that we are doing our part to help save the planet.
Attention, everybody. We're going to forget that environment stuff and use a chip for computer games. Back to work.
3DFX PC accelerators. So powerful, it's kind of ridiculous.
Blast is breaking head off!
So again, here's that's sort of a funny version of this, but the point is that we're constantly changing in the way we think about how technology is going to be used and what it's going to be used for, and the notion that a lot of the uses of technology would in fact be for entertainment, was not something that if you went back and talked with John von Neumann or some of the early pioneers in the field, they would necessarily have thought of. Now, sometimes you predict the future very well, but you still don't necessarily wind up being the beneficiary of your prediction. I'll give you a Microsoft example. This is a slide I personally used in a talk I gave in 1993. Actually, the slide itself came from another gentleman that I worked for at the time, Nathan Myhrvold. And he laid out this vision for what he described as the wallet PC. I mean, we would see this as a modern cell phone. And you can see this again from 1993. All the elements of the modern cell phone were in this device as it was described. Now, of course, back in 1993, we didn't have the technology that could create such a device. But because of this vision, at Microsoft, we actually created a group even in those early days, to pursue this idea. And this group created the early versions of what became the Pocket PC from Microsoft. The compact iPac was an example of that from the late 90s and early 2000s. It became what became Windows Mobile. But what was not foreseen was that these types of devices would become much more popular, much more prevalent with the introduction of another technology. In this case, it was the capacitive display that allowed people with their fingers to interact with the device. And it was Apple, with the original iPhone, that was really the beneficiary of that innovation. They were able to take the capacitive display technology that had been invented by others, merge it with the devices that they were designing, and suddenly they had a completely different kind of device. It still had all these elements, but because of the interactivity that was created by the capacitive display, they were able to develop a tremendous market for what they did. So you can sometimes see the future, work hard at it, and not necessarily be a beneficiary of it. In other cases, you see the future, you do the right thing, but you may not be doing it at the right time. It may not be the right time to be making those investments or doing that work. This is an example from 1994. It's a system that I built. It was one of the projects we had early on at Microsoft Research, working with Microsoft product teams. And we built in 1994 and deployed in 1996 a fully interactive fiber optic to the curb TV system. It was deployed in a suburb of Tokyo in Japan in conjunction with NTT and NEC. Each home had over 100 megabits per second of data access. All the elements that you might think of as an interactive TV system were in that system. Unfortunately, it was the wrong time, because we were developing that system and bringing it to fruition in roughly 1996, thereabouts. Well, it also turned out that in 1996, the United States passed sweeping telecom legislation that dramatically changed the incentives in the telecom industry. And when we were doing this work, there was a lot of interest among these companies in investing in what was in those days described as the information superhighway and interactive television. Suddenly, they became much more interested in buying each other and merging and changing the way they thought about their businesses in a different way. And it was really 10 years later when these types of systems became relevant again. So in that case, it wasn't so much that it was the wrong time for the technology, but it was the wrong time because of legal and tax constraints or changes that existed in the system. And those can be significant, and they can have a huge impact on the release of a technology. So the reason why predicting the future is really hard, or decoding the future is really hard, is technology really doesn't move in a straight line. New approaches catch you by surprise. So what was, even though Thomas Edison had a sort of a negative view of alternating current, in part because he owned all the patents on direct current, it was also the case that it didn't seem like it made a lot of sense until the introduction by Westinghouse of the step-up and step-down alternating current transformer, which suddenly allowed you to send enormous amounts of power, long distances over relatively thin wires. And that changed the value of the technology tremendously and caused alternating current to become the standard that it is today. It's hard to predict how cultures and individuals will react to technology. Just think of the cell phone. When the cell phone was created, people actually thought that it would be used for voice communication. people would call each other. But many of you are students. You probably don't call each other very often. You're mostly texting. You're mostly sending email. You're mostly reading the web. The uses of the cell phone changed dramatically as time went on because, in fact, it could do different things. And so even though it began as a technology that was sort of an imitation of the original telephone, it turned into something very, very, very different. And I've mentioned issues about tax policy. So I was born in 1951. So this is an indication of how old I am. And here's some examples of things that existed in 1951. My parents' car looked a lot like the car in this picture. This is a Ford Victoria. We did have a radio that looked exactly like that. That's a 1951 radio. Our TV looked exactly like that TV. In fact, I have some pictures of me as an infant, near a TV that looks exactly like that. Interestingly enough, in 1951, the first UNIVAC computer was sold. In this case, it was sold to the U.S. Census Bureau. So even in 1951, as I was being born, suddenly computing was becoming relevant. Of course, I didn't know that. I was growing up in a small town in a poor area in rural America. And so I didn't see a computer until I went to college. The first computer I ever worked with was this. It was an IBM 360-67, big mainframe style computer that they had at Stanford University where I was a student. And that's the first computer I learned to program. Now, luckily for me, I was able to work in the very early days with the Xerox Alto. This was the very first personal computer, created around 1973. And my original graduate student career in computer science started at the University of Rochester in 1974. And we were the first people outside of Xerox PARC to have access to the Xerox Alto. In fact, here's a picture of me from this is 1975, typing on a Xerox Alto. I had more hair. I still have that jacket, but I don't wear it. But I still have it. Now, the world's changed enormously in that period of time, and I've certainly personally been the beneficiary of that change. You can see some of the differences here between the Xerox Alto that I programmed on, which literally its performance was 1/10 of a MIP. Right? Today we talk about billions of operations per second. This was 100,000 operations per second. Very slow by modern standards. In fact, really, really slow. Microsoft Surface Pro 2 today, is 132 billion instructions per second. So it puts that all very much in perspective. Storage, of course, the Alto had a very small amount of storage. And in fact, even in the mid-1980s, the entire planet had less storage capacity than a typical memory stick today. So that puts things in perspectives. You could, however, do some pretty amazing stuff. This is a screenshot from the game that Han mentioned that I developed as a student when I was at the University of Rochester for the Xerox Alto. It was a game called Alto Track, and was really the first Ethernet space combat game. And it helped to define what was eventually the multicast standard for the modern Ethernet, because this game required multicast in order to work. And so I developed a technique for using these devices and using them in a multicast way in order to make the game function properly. So it was a lot of fun. And back in those days, this was very, very useful. Interestingly enough, more than 20 years later, I actually developed another game. This was for Microsoft, but it was based on the same game. It was based on the same code, obviously very much improved and changed. The game was called Allegiance. You can still play it on the internet. It's actually still available, and there's a community of people that still do play this. Clearly, graphics and computing power changed a lot in the meantime. But I am very proud of the fact that the game got very, very good reviews. In fact, it got the best reviews of any Microsoft game until Halo. So I thought that was a great statement about that. But again, it goes back to the fact that I had early access to some very powerful computing, at least for that day. Now, I was also present during a period, I think, of tremendous opportunity in creating operating systems that would define the future of computing and certainly of personal computing. When I was at Carnegie Mellon University, I created a couple of different operating systems. First, one called Accent, which was an operating system designed for a sort of next-generation Alto-like device, a personal computer that connected onto the internet. But I also created, after that, working with my graduate students, a system called Mach, which took the key concepts from Accent, but carried them over into a new world of multiprocessors. So it didn't just work in a network environment, but in fact, it worked across both small-scale and very large-scale multiprocessor systems. In fact, I coined some terminology because no one really had terminology for describing the different kinds of multiprocessor systems in those days. And so I coined the terms UMA, NUMA, and NORMA. The one that's preserved the most out of those three is NUMA. But I needed to be able to describe to people the different kinds of computing architectures that the operating system we created would work on. And so I needed to have names for those things in order to do that. Now, Mach went on from being a system built in a university environment to having an enormous impact even on on the things that you do. It became the basis for something called the Next computer that Steve Jobs created in the late 1980s, and became from there the basis for Mach OS. So Mach OS X or 10 was based on the Mach operating system kernel, and all versions of the Mac and iOS since then have incorporated elements from that system. It also became the basis for many versions of Unix, and in fact, Mach was the basis for what was called OSF1 or eventually digital Unix, compact Unix, and it was incorporated into many different other versions of Unix, and the technologies and ideas were adopted into even versions of Linux today. And of course, it had an impact on Microsoft as well. The early versions of Windows NT incorporated some of the key concepts from Mach, and in fact, the project that started Windows NT was originally based on the ideas that came out of the Mach work. So it's had an unusual amount of influence over the years. So probably you're using code that I wrote back in 1983 on some device, whether it's an Apple device or a Linux-based device or a Windows device. You're probably using code that I've written. Now, why was Mach so successful? Why did it have such a big impact? And I think this is illustrative of the question, why do some technologies succeed even when they're doing things that you never would have imagined? So obviously, when I began work on the Mach operating system back in 1983, it certainly would not have occurred to me that it would eventually be used on a cell phone. And that's because there weren't any cell phones. I had no idea what a cell phone was because there weren't any back then. But it eventually became used for things that it was not originally intended because it was designed to be extremely flexible. And it was that extensibility and flexibility that had a huge impact on its adoption. So certainly the ability to support other systems was important, because in every instance where Mach was used, it was used first as the basis for something else, a version of Unix or Mac OS or DOS or Windows. It had a very flexible architecture. Remember, it was designed for a multiprocessor environment. And so as a result, it could span many different kinds of computers, both small and large. Again, that gave it an advantage. So just to tell you a story, this is the man that actually did the original Mac OS X and then went on to create the original iOS was Avi Tevanian with his team. And Avi was my graduate student at Carnegie Mellon University working on Mach. And he tells the story of how iOS came into existence. So originally, when the first iPod Touch was being designed at Apple, they were planning to use some kind of specialized real-time operating system. And Avi and his team thought that this was crazy. They felt that it would be better to leverage the work that they've invested in the Mac and the Mac OS. But everybody told them, no, that wasn't going to work. The system was too big. It wouldn't be adaptable for that purpose. So he and his team, working really without permission as a Skunkworks project, took it upon themselves to create a version of the Mac OS at that time, based largely on the Mach kernel, that could run on what was then the prototypes of the iPod Touch, and could then become the basis for a larger kind of system. They were successful in that. They were able to convince the company to go in that direction. And because of that, the Apple devices, whether it was starting with the iPod Touch and moving on to the iPhone and the other devices, had a much more flexible, much more supportive, underlying systems technology. And probably that was one of the key success factors that made those devices work. Now, after I left Carnegie Mellon, I went to start Microsoft Research. I think Han already mentioned that I've been the founder of Microsoft Research. And I think, again, you go back to the investments that we made at Carnegie Mellon in basic research. Those investments paid off handsomely in the sense of having a huge impact on products, on industry, even though we were not working within a company. When I went to Microsoft, my idea there was to go to Microsoft to create that kind of research environment where we could create the kinds of artifacts, intellectual artifacts, and technologies that could have a huge impact on not just Microsoft, but on the broader corporation. It's interesting that Microsoft even wanted to do it. This slide points to the fact that it was really a decision by Microsoft Board of Directors in 1990 to make an investment in basic research. I was contacted in 1991 to become the first director. And when I got to Microsoft, I had really a philosophy with three key elements. These were the basis for the mission statement that we use even today within Microsoft Research. And those elements, I think, are a statement about the things you need to do to make the investments that do allow you to create the future. First was expanding the state-of-the-art in the areas that we do research. And for me, that's always been the most critical part of what a research organization does, is we move the frontier forward. We learn, we test, we try, we fail, we understand what works and what doesn't work. Once you understand what works and what doesn't work, then you can rapidly take your ideas and try to move them into products. And that's, of course, what we do within Microsoft Research as well. But ultimately, this is about the future. It's about making sure that not just Microsoft has a future, but the field of computing has a future. I mean, the reason that we work as researchers in computing is because we want to create a future. We want to change what people will be able to do. We want to be able to solve the key problems that exist in society and make people's lives better. So obviously the organization has grown. I think Han probably referenced this as well. Microsoft Research Asia, started 15 years ago. And I think it's interesting for me to think back today on the creation of Microsoft Research Asia, because when we started it, it was very controversial, not just in the United States, but in China. And it wasn't so much that it was politically controversial, but that it was technically controversial. People asked the question, could you create in China the kind of basic research organization that we had in the United States and that existed in places like MIT or Stanford or Carnegie Mellon? And I think we've proven over the last 15 years that not only can you do that, but we have done it. And Microsoft Research Asia today is one of the premier basic research organizations in the world in its own right, not just as part of the larger organization. This slide talks a bit about some of the key things that I did to try to create an environment where researchers could be successful. And frankly, a lot of these ideas I took from my time as a university professor at Carnegie Mellon University, where I really felt that that type of environment that encouraged collaboration, that encouraged risk-taking, and encouraged the ability to work as groups to solve problems, that was the kind of environment I wanted to have within Microsoft, and that's what we've been able to do. I've also felt strongly over the years in investing in universities. And really, this event is an example of that, where we have made a huge investment over the last 15 years in reaching out and trying to work with students and talking to students about the value and the potential of changing the world by working in the field of technology. This just talks about some of the, we've clearly had huge impact. This is a really old slide from 2009. But, you look at the conferences and the things that we've done, there's just enormous amounts of change. Now, I talked originally about wanting to be able to impact, the real world. And Microsoft Research has changed every product that Microsoft produces. Every product has something from Microsoft Research. And that's really a testament, I think, to the opportunities that exist in a company like Microsoft and the fact that basic research really can make those kinds of contributions. Now, when people talk about the impact, why do you make investments in basic research? They'll often talk about these things. They say, oh, well, a company invests in basic research because it's a source of intellectual property and new products. And certainly we do that within Microsoft Research. They often say, well, you're a problem-solving group. If you've got smart people, PhDs, they're going to solve problems. They're going to find solutions. And we do that. I love solving problems. I have loved solving problems since I was a little boy. I still love solving problems. That's what I do. And that's a great value to a company like Microsoft, because we have lots of problems that need to be solved. Obviously, early warning system, that's a great value too. But the real value of investing in basic research and the real value for you in putting your career into creating new ideas and new technologies and doing research is the ability to survive. Not just, for Microsoft, it means the ability of Microsoft to be agile and to be able to change and be able to survive. For society, it means about society being able to survive. Vannevar Bush, who helped create the National Science Foundation, pointed out that the real reason for the U.S. government to make investments in basic research was to make sure that as a country we could survive if there was a new war. We'd just come from World War II, where technology was really important. If there was a new war, or if there's a famine or a disease, you need the smart people and the reservoir of ideas that let you adapt, that let you change, that let you survive. And that's as true for a society, it's as true for the planet, as it is for a company like Microsoft. Here's a very simple example. This is actually from 1992. We began work in 1992, and I was involved in this, in developing a technique for reducing the working set size of programs. So basically, trying to reduce the amount of storage needed for computer programs in those very small computers of those days. Now, the technique we developed worked for 32-bit code. And we were very proud of ourselves. And it was very early days for Microsoft Research. And we talked with the product groups. And we assumed the product groups would be very interested in what we were doing. And they were certainly very, very interested and very polite. But they had no use for the technology. I mean, each meeting would end with the person from the product group saying, you guys are very smart. But we don't have that problem because we don't have 32-bit code. I mean, that was back in 1992. In 1992, you only had 16-bit code in major products. And also, there was another element of their concern, which was that they assumed that memory sizes and memory prices were going to continue to go down because of Moore's law. And so they figured when they did have 32-bit code and when they were going to be able to use this technology, it wouldn't be important to them because memory sizes would be so big that it wouldn't be interesting. Well, what happened, and you see this on that little blip in the slide around 1992, 1993, and so forth, is that not only did memory prices go through a period where they didn't really change very much, but in fact, they actually ticked up just a little bit and had to do with trade issues between the United States and Japan and Asia, and there were a lot of other reasons why it happened. But as a result, in 1995, when Microsoft was about to ship Windows 95 and Office 95, which were 32-bit products, that system wouldn't fit in the computers that existed in those days. Those computers only had 4 or 8 megabytes of memory. That's megabytes, not gigabytes. And our software had been optimized for 16-bit code, and 32-bit code took up twice as much space. Because in Microsoft Research, we had developed the technology to reduce the working size of programs by a factor of 2, we could take Windows 95 and Office 95 and make them run in those smaller computers. That allowed Microsoft to ship Windows 95 and Office 95 when otherwise it wouldn't have been able to in that year. It allowed us a tremendous lead on our competitors, which they never recovered from. So it was a huge financial impact to the company, but a huge strategic impact on the industry. One research idea. And that's what can happen, is when you need a great idea, when you need a technology, suddenly it might be there if you've made those investments. Well, Microsoft Research, I think over the years, has had many firsts. I've just listed a few here. Certainly, we had the first terabyte database on the web, something called a Terra server, the first large-scale use of program proof technology in something called SLAM, which became the static driver verifier, the first practical use of 3D computer vision as an accessory, the Kinect device that I'm sure you're all familiar with, the first major use of program synthesis, the ability to automatically create a program from examples, and that's in the flash fill feature in Office 2013. And just last year, the first real-time speech-to-speech translation on stage, which I had a chance to do. This just gives you a sense of the Terra server, which became Virtual Earth and Bing Earth. Eventually, the technology was used to create what today is the Worldwide Telescope. Here's flash fill, which basically is a technology where in Excel, where you give the system a few examples, and then it can effectively write a program that will do what you wanted it to do. And a tremendous feature, and I recommend you experiment with that and play with it on your own. Of course, Connect, Microsoft's just about to release this second version of Connect with Xbox One. Again, I think that's going to be a huge product for the company, but also it's going to set even a new standard for real-time 3D computer vision. The precision on the new Connect 2 is tremendous. You can detect small movements of fingers. You can detect small movements of your body and gestures that you were never able to do in the earlier versions of Connect. And it's going to change the way people think about interacting with their computers once again. And the last thing I'll mention is something I did last year on stage in Tianjin, which is to, in some sense, this was a culmination of something I'd been wanting to do for a very long time, and I've been trying to get teams within Microsoft Research to do with me for a long time, which is the ability to be able to do simultaneous translation from one language to another. Now, I don't have the setup here, but I do have a short video clip so you can see what that was like last year when I was on stage and did that. Now, the last step that I want to be able to take in this process is to actually speak to you in Chinese. Now, the key thing there is we've been able to take a large amount of information from many Chinese speakers and produce a text-to-speech system that takes Chinese text and converts it into Chinese language. And then we've taken an hour or so of my own voice, and we've used that to modulate the standard text-to-speech system so that it would sound like me. So what you see now is the result of that change. I'm speaking in English, and hopefully you'll hear me speak in Chinese in my own voice. Again, the results are not perfect. There are, in fact, quite a few errors.
结果并不完美。他们提醒小数改错误。
There's much work to be done in this area.
在这方面有很多工作要做。
But this technology is very promising.
用这个技术很有希望。
And we hope in a few years that we'll be able to break down the language barriers between people.
数年后，我们希望能够打破人们之间的语言障碍。
Personally, I believe this is going to lead to a better world.
我个人认为这将导致更好的世界。
I hope you enjoy the rest of the presentations today.
希望今天你喜欢其他的讲座。
Thank you.
谢谢。
Well, for me, that was the culmination, not just of a, long career in computer science, but also a dream about the kinds of things that we would be able to do with the technologies we created. I will point out I'm wearing exactly the same suit today and exactly the same tie. So what does the future hold? Well, obviously, I think I tried to explain in the beginning of the talk that it's very difficult to know that. Now, strictly speaking, I should know because I'm a character in a science fiction novel. There's a character named Nathan Rashid, in a novel called Slant by Greg Bear. And that character is sort of a half Nathan Myhrvold, was a guy I worked for, and half me. And that character creates the world's first true artificial intelligence and helps to save the world. So maybe that's what will happen. But I kind of doubt it. I think the key thing to realize and recognize is, as scientists, it's not that we create the future. We create the raw materials. We create the pieces from which a future can be created. At the end of the day, it's really you, it's really me, it's us as a society that create the future, that determine how these technologies that we create during the course of our lives and our careers are going to be used and going to be taken advantage of. Thank you very much.